Hello everyone. Today I introduce uh, title Critical Training to Class L2 SVM support machine by several variants of conditional gradient. SVM is a famous algorithm for classify data with labels, and this is this is find the best separate hyperplanes between data points, and these data vectors is called support vectors. And support vector machine has some weakness. First, its performance is low down on the very large datasets, and is impacted by choosing the wrong kernel. For example, the linear separable dataset will not work with non-label kernel, and also the SVM perform uh, poorly on unbalanced dataset, which is model will bias uh, about the instance last dataset set. And to eliminate the weakness of support vector machines, RSVM is a version can reduce the effect of the dataset size to the performance of SVM. The idea is symbols. We choose the random success matrix data from original data matrix. For example, we have the data matrix R, which in dimensions m by n. This is the class dataset, so we just use 1% to 10% of this data matrix to perform training data. This step to choose just we should random choosing sample from dataset. We then calculate the distance between each row, and we pick the minor subset of the original data matrix by choose tolerance. If the distance over the tolerance, we will choose this sample in to make a new training data. In this work, I solve the L2 optimization problems of SVMs. Here, this is the formula of the convex optimization problem. This where in this formula, W is the parameter of the original HVMs, and P is the bias term. C is the constant, and in L2 problem we add the slack variable C, which is greater than 0 for each training data in the dataset. We have the constraint of this problems is macros of each sample will be greater than the machine of the average machine in the dataset minus to the slack variable for each sample. Then we will solve this L2 problem by uh, by using the method to optimize minimal enclosing ball problem. We need to transfer the formula of the L2 problem to the formula of the minimal enclosing ball problem, and then apply the conditional gradient methods on this math problem. The minimal enclosing ball problems is in this slide. We have given the data bond is say in the data matrix S. We have the n data bond, and where each data bond is n is the n dimensional vector whose and is associated with the mu chase Lagrange multipliers. We solve this problem use a Lagrange method. This problem which contains the mu parameter will be greater than 0, and the sum up on the coordinate of vector is 1. So we can see mu is in terms of the simplest. Then to solve this, we will embed this formula into dot product space. In this space, we replace the S data matrix and dot products by the kernels, and we replace the mu parameter by the alpha parameter. This is not the new method, but I summarize here to understand the ideas and how to apply the BCG algorithm to solve this problem. So we can see here we will trick the mu in equation 2 and alpha to perform optimization in this math problem. The equation number 2 and number 3 is similar if only if we set the kernel case title satisfy some constraints. So you can see here this in equation 5 the constraints is the K kernel K title will be some factor calculated from the K kernel which is used in original APM, where CAJ is equal 1 if the samples if the H index equal J index, otherwise it's equal to 0. The kernel is satisfied this constraint is Gaussian kernel, which defined in equation 4. After the optimization on the equation 3, we will got the alpha and we can derive the decision SVM decision function from alpha and kernel case. We can see H is the decision function of the SVM is calculated as in equation 6. Then how we optimize the equation tree using the BBC algorithm. First, to use the BBC algorithm, we need to define the primal function and the gradient function. The primal function we use here is mu rainbow we dot product with dramatic tree and with mu. The gradient function in the form in the equation 9. This I will use the grammatic for faster computation instead of use the data matrix H. This is the simplest BBC algorithm require implementing linear optimization oracle instead the simplest. There's linear optimization oracles on the standard index if we can find ones of the vertex on the simplest which minimize the dot product, minimize the gradient value. To use implement this algorithm, I use Python and C++. The C++ has convenience of large symbol bar vector. It stores key values for only non-zero values for faster computation. To test the SVMs, we use the MNIST dataset. Every data record is scaled by dividing by 255. The performance scores is evaluated on datasets with ratio 0.7 for datasets and 0.3 for datasets. The Gaussian kernel uses with sigma equal to 0.2 and the RSVM is controlled by sampling 10% data from transit to match optimization. This slide shows the primal progress of three variants of conditional gradients to train the SVMs. In the rest is conditional gradients and green is the lazy blend conditional gradient and the blues is non-lazy blend conditional gradient. We can see here the new algorithm blend conditional gradient BCG and lazy BCG have better converge rate than the CG algorithm. And SVM model trained by BCG achieved 100 resistance score on test set after 100 iteration. Thanks for some words reviewed work. This is work is not new, but I applied the pairwise conditional gradient to training the RSVM. This is some published repository, my repository on for this title. This is my implementation for conditional gradient. Here is the function the linear minimization oracle. This is the BBCJ Lazy algorithm, and this is the result compare between three algorithms. Thank you for hearing and see you in next title.